So I want to start by saying something kind of controversial, but the screen you're looking at right now, it's basically lying to you.
Oh, totally. But I mean, it's a comfortable lie, right? We kind of want to believe it.
Exactly, because when you write, a simple line of code that says print hello, and then the screen obediently flashes hello, you feel like you're looking at reality.
Yeah, you feel like the digital world is this perfectly transparent window.
Right, like your intention just maps perfectly one-to-one with the result.
But the second you move past just like printing text and you actually start trying to build high-fidelity physical simulations, that transparent window just shatters.
It really does.
You realize pretty fast that the pixels lighting up on your monitor are not the actual physics. They're just an illusion.
And honestly, realizing that is the first step into this computationally and, well, philosophically terrifying landscape. So, welcome to this deep dive, everyone.
Glad to be here.
Today, we are sending a very specific, incredibly enthusiastic welcome to our target audience, the Bus and Sigma scholars of Edward Littlehei.
Oh, yeah. We know your reputation, scholars.
Elite intellect, insane curiosity.
So we are definitely taking the training wheels off for this one.
We are. We're laying out a massive mission today. We aren't just going to talk about, how to code a bouncing ball in Python.
No, we are going to explore how to basically architect reality itself.
Which sounds huge, but we're going to do it. We're merging the Carnegie Mellon University, so CMU, their CS Academy CPCS MVC coding framework, with the foundational quantum philosophy of Albert Einstein, Niels Bohr, and John Bell.
It is quite the stack of sources, and we're going to back it all up with some of the most beautiful, complex math out there.
Like Riemannian manifold optimization?
Right, and dissipative mechanics, and even the architecture of gauge equivariant convolutional networks.
Which sounds like a lot, I know.
It does, but don't worry. We're going to translate all of that graduate-level math directly into the Python code you write every single day.
And here is the real aha moment we're building toward, right? We're going to show how a common everyday coding error in a high school physics simulation.
What CMU explicitly calls an MVC violation.
Exactly. How that specific error is actually fundamentally mathematically identical to Werner Heisenberg's incredibly flawed 1926 philosophy of quantum mechanics.
A philosophy that Albert Einstein literally had to publicly dismantle.
It is a stunning parallel.
It really is. I mean, if you understand why your CS Academy code crashes when you put a state mutation in the wrong function, you fundamentally understand the greatest debates in the history of quantum mechanics.
So let's just jump right into that history, because we have to start with the philosophical blueprint before we touch a single line of code, right?
Definitely. We need to travel back to the spring of 1926.
Berlin.
Right. Werner Heisenberg is riding incredibly high on his, new quantum mechanics.
He had just introduced matrix mechanics, which was this radical new way to calculate quantum phenomena.
Yeah, and he's giving a lecture to a distinguished body of physicists at the University of Berlin. He is the young rock star of physics at this exact moment.
And Albert Einstein is sitting right there in the audience.
Just watching him, yeah. Einstein is intrigued, and he actually invites Heisenberg to walk home with him so they can debate these new ideas.
Which is amazing. Heisenberg recounts this walk in his memoirs, and the dialogue they had is just incredible.
It's intense. The second they get indoors, Einstein basically goes on the offensive.
Right. He challenges Heisenberg, saying something like, "You assume electrons exist inside the atom, but your math completely refuses to consider their orbits. Why?"
And Heisenberg gives an answer that reveals a very specific, very dangerous philosophical trap.
What does he say?
He says, look, we cannot observe electron orbits inside the atom. It's just impossible. We can only deduce frequencies and amplitudes from the radiation that the atom emits.
Okay, so he's basing it all on what he can see.
Exactly. Therefore, Heisenberg claims, since a good physical theory must be based only on directly observable magnitudes, he restricted his math strictly to those observable radiation frequencies.
He's basically saying, if I can't see it, it doesn't belong in my math.
Wow.
Which, bringing it back to programming, is like saying, if I can't print it to the console, it shouldn't be in the code.
That's a great analogy. He even tries to throw Einstein's own theory of relativity back in his face.
Oh, right. He says, didn't you do the exact same thing? You stressed absolute time can't be observed, only clock readings matter.
Yeah, Heisenberg was subscribing to strict verificationism.
Which means what, exactly?
It's the idea that the meaning of a concept is entirely dependent on your ability to directly observe it. If you can't build an observation language around it, it's garbage.
But Einstein's rebuttal just completely shatters this, doesn't it?
Completely. He looks at Heisenberg and says, it is the theory which decides what we can observe.
Wow. It is the theory which decides what we can observe. That is a massive paradigm shift.
It reverses the entire flow of logic. Einstein forces Heisenberg to realize that observation is not this simple, clean process.
Right, like think about what happens when you observe a radiation frequency.
Exactly. A physical phenomenon occurs. It interacts with a measuring apparatus, maybe a spectroscope.
Okay.
The apparatus undergoes physical changes. Those changes emit light, which travels by complicated paths into your eyeball, hitting your retina.
And then it's processed by your optic nerve.
Right. Interpreted by your brain and finally fixed in your consciousness.
So Einstein is basically telling him you have to assume a massive complex theory of how optics, electromagnetism, and human neurophysiology work across that entire path just to claim you've observed a reading on a dial.
Bingo. You can't start with the observation. The observation is the absolute very last step of a hidden computational chain.
You cannot build the foundation of reality out of what you see.
Precisely.
I want to break down exactly how Einstein mapped this out because our sources point us to a letter he wrote much later, right, in 1952.
Yeah, a letter to his friend Maurice Solowin.
Right, and in this letter, Einstein actually draws a schematic diagram of how science and reality is architected.
He breaks it down into three main components, A, S, and E.
This is the architectural blueprint we are going to use to code our simulations today. So let's start with A.
A stands for axioms. This is the system of fundamental rules and the true hidden state of the universe.
Okay.
Psychologically, Einstein says, these axioms are inspired by our experiences, but logically, they are completely distinct.
Meaning there is no logical path from what I see to the fundamental laws of reality.
Right. You cannot derive the law of gravity just by watching an apple fall.
Because watching the apple is just the experience.
Exactly. The law itself is a free invention of the human mind meant to model the hidden backend.
Okay, so A is the hidden backend, the raw variables. Then we have S.
S stands for specific statements.
And what are those?
These are the rigorous mathematical deductions you make from the axioms. If the axioms define how gravity and mass interact, the statements are the equations predicting where a specific cannonball will be at exactly 2:04 p.m.
But crucially, these statements are still theoretical, right?
Yes, they're pure math.
They aren't real life yet.
Exactly. Which brings us to E.
E stands for immediate experiences.
These are the messy extralogical observations of our human senses, the actual visual image of the cannonball kicking up dirt when it lands.
And the author of our source paper on this, Tim Maudlin, points out that the absolute hardest part of physics is the gap between S and E, right?
Oh, totally. The gap between the pristine mathematical theory S and the messy human experience. E. Einstein said they are connected by intuition, but that is a massive, terrifying gap.
Because, I mean, no physics equation has ever successfully calculated the entire path from a physical event through the human eyeball into subjective consciousness.
Right. We don't have the math for consciousness.
Precisely. So to bridge this gap, to actually test if our hidden backend A is correct, the theoretical statements S must be forced to describe what John Bell later called macroscopic local beebles.
I love that term, local beebles.
Yeah, things that can be.
A local beeble is an intersubjectively testable thing that exists locally in space and time.
Like the cannonball sitting in a crater.
Or a literal physical pointer pointing to the number 5 on a dial. You don't test a quantum theory by asking a scientist how they feel about an electron.
Right.
You test it by seeing if a macroscopic local beeble, a dot of ink on a piece of paper, a flash on a screen, appears where the math said it would.
Okay, I want to ground this for our Sigma scholars.
Okay.
Heisenberg wanted the universe's source code written entirely in print statements.
He only wanted the output, the screen, the E.
Right. But Einstein is saying, no, you need a hidden back-end logic, the axioms, the A, that calculates the physics entirely in the dark.
And the print statements, the observations, are just a superficial byproduct of that hidden calculation.
That is the perfect summary. But I'm going to push back here for a second.
Okay, let's hear it.
This all sounds great for a philosopher writing on a chalkboard in 1926. But we are talking about building a physics engine on a high school laptop. If Einstein is right, and the true state of reality is a massively complex hidden backend, how do we actually build that? Reality has infinite variables. Every single atom exerts a gravitational pull on every other atom.
That's true.
So if I have to code the true backend of the universe to get a valid observation, my simulation is going to freeze before it even compiles.
And this brings us to a brilliant concept from the text that answers your exact question. The fallacy of Laplace's demon.
Ah, Laplace's demon. This is the thought experiment proposed by Roger Bouchovich and later popularized by Pierre-Simon Laplace.
It is essentially the ultimate godlike intelligence.
Right. The thought experiment goes, if an intelligence knew the exact position and velocity of every single atom in the universe at a given instant,
And it had infinite computational power to analyze that data using the laws of physics?
then it could predict the entire past and future perfectly. For this demon, nothing is uncertain. It is the perfect physics engine.
And you're saying we shouldn't try to be Laplace's demon when we code?
I'm saying you cannot be Laplace's demon. The text details 5 specific, insurmountable reasons why this is a complete impossibility in reality.
And why human scientists and our programmers must rely on approximations and idealizations instead.
Let's run through these 5 failure points, because understanding why the demon fails is actually crucial to understanding how we must structure our code later.
Okay, number 1. The demon needs a complete, microscopic physical description of the entire universe as its initial data input.
Which is logically and physically impossible. Imagine trying to run a perfect virtual machine of a laptop, perfectly emulating every single byte of storage and every single transistor inside that exact same laptop.
You'd run out of memory instantly.
Exactly. No subsystem of the universe can contain a complete, perfectly detailed description of the whole universe because the storage medium itself is inside the universe.
It creates a physical infinite regress. You cannot store the universe inside itself.
Okay, failure point 2. Compute limits.
Right, let's say you magically acquired all that data. The calculations are mathematically intractable. Think about the three-body problem.
Oh yeah, where humans and supercomputers struggle to calculate the chaotic gravitational interactions of just 3 celestial bodies over long periods.
Now scale that to the interactions of septillions of atoms. The compute required just exceeds the thermodynamic capacity of the universe.
It's impossible. Okay, failure point 3. Horizons. I love this one because it's purely relativistic.
It really is. The speed of light is a hard limit on information.
So if a massive universe-altering supernova happened 1,000 light years away and the light and gravitational waves are heading toward Earth right now,
We cannot possibly know about it today. So if we run our simulation of tomorrow, it will be wrong because we were blind to data outside our observable horizon.
because causality is bounded by light cones.
Exactly.
Failure point 4. Large degrees of freedom and chaos.
Even if you isolate a simple box of gas, the number of physical degrees of freedom, the ways those molecules can move, is astronomical.
The state is so delicate, so perfectly balanced, that the mere act of measuring it to get your initial data will irreversibly disturb it.
It's the ultimate butterfly effect.
And finally, failure point 5. Quantum indeterminacy.
Right. The fundamental dynamical laws of reality at the quantum level are not strictly deterministic. You can only calculate probabilistic expectations, not the absolute clockwork certainty that Laplace's demon requires to predict the future perfectly.
So, because we cannot be Laplace's demon, because we face memory limits, compute limits, horizons, and chaos, we cannot simulate the universe atom by atom.
We have to separate the universe into manageable, isolated sandboxes.
We have to use specific, idealized architectures, and that necessity for architecture brings us directly to how we actually write code.
Which leads us to the fatal flaw of how beginners are usually taught to simulate physics.
This is where the rubber meets the road. I want to look at the first coding concept from the CMU CS Academy sources. Standard CS1 persistent object mode.
Scholars, if you've ever taken a basic intro to coding, this is how you learn to draw on a screen.
It is highly intuitive. It's designed for absolute beginners.
Right. In CS1 mode, you call a constructor function like rect or circle, and a persistent object is instantly instantiated and placed onto the canvas.
You type circle, 200, 250, and boom, a circle with a radius of 50 appears in the center of the screen.
And it stays in the computer's memory. It remains permanently visible on the screen until you explicitly write a line of code to delete it.
But if you want to make that circle bounce across the screen, how do you mutate its state?
You alter the properties of the visual shape directly. Inside a timer loop or a key press event handler, you literally grab the shape's visual property and change it.
You write code like shape.centerx plus equals dx. You are directly grabbing the drawing and shoving it to the right.
Now, analyze this from the perspective of Einstein's ASE diagram, the axioms, statements, and experiences. Where is the fundamental mathematical state of the physics stored in this CS1 model?
Well, it's stored implicitly within the visible shape instance itself on the canvas.
Exactly. The thing you see is the thing holding the data.
And the source material outlines why this is a fatal error for high-fidelity physics.
It totally is. When you have hundreds of objects bouncing around, calculating complex collisions, directly mutating the visual properties on the canvas causes the rendering engine to choke.
It accumulates artifacts, doesn't it?
Yeah, you get unintended shape overlap. The physical boundaries of your objects literally break down because the drawing engine can't keep up with the math.
I want to stop you right there, though, because I have to defend CS1 mode just for a second.
Okay, go for it.
When I was learning to code, tying the math to the visual object was the only reason I understood what was happening. It makes sense to the human brain. If I want to move a block, I push the block. I don't calculate the block's theoretical position in a hidden void and then wait for a magical rendering engine to catch up.
I get that.
So CS1 is intuitive. Why are we demonizing it?
Because your human intuition is exactly what Einstein was fighting against in 1926.
Oh.
The philosophical failure of CS1 mode is profound. By storing the data inside the visual shape, CS1 mode entirely conflates the axioms, the hidden mathematical state of the physics, with the experiences, the drawn pixels on the screen.
It is exactly the trap Heisenberg fell into.
It is verbatim Heisenberg's mistake. Heisenberg said the theory must be based only on the observable properties. CS1 mode says the physics state is the observable drawing on the canvas.
And if the drawing is the state, the physics break down when things get complex.
Because you are trying to do mathematical derivations S on the sense impressions E directly, without a hidden back-end A.
You're saying the universe does not store a baseball's kinetic energy inside the photons that are bouncing off the baseball and hitting my eye.
Exactly. The universe stores the kinetic energy in its hidden fundamental state. The photons hitting your retina are just the output, the print statement.
When you write shape.center x plus equals dx, you are trying to alter the universe by manipulating the photons.
It's philosophically backward, and mathematically it causes accumulation errors and crashes.
Okay, you've convinced me. If tying the physics to the persistent drawing is a philosophical and computational disaster, how do we escape? What is the architectural alternative that separates the hidden reality from the observable reality in our code?
We abandon CS1 mode entirely. We upgrade to the College Programming and Computer Science Framework. We move to strict Model View Controller Architecture, MVC.
And scholars, the source report details exactly how unforgiving the CMU CPCS strict MVC framework is. In this mode, those persistent constructors we just talked about, the rect and circle,
They are completely banned.
banned. If you try to instantiate a persistent shape object inside your view or controller logic in CPCS MVC mode, the system throws a fatal execution error. It just refuses to compile.
The system physically polices Einstein's philosophy. It basically says, no, you cannot conflate the back end with the print statement.
To understand why MVC is so profound, we have to bring Niels Bohr and John Bell back into the conversation from the Maudlin paper.
Right. Bohr, one of the founding fathers of quantum mechanics, stated that experimental outcomes, the things we actually observe, must always be described in classical terms.
We have to use the language of macroscopic local Beebles to describe a measurement, even if the underlying reality is a bizarre, unobservable quantum wave function.
And John Bell pushed this further. He argued that these macroscopic observables, the pointers on a dial, the ink on a paper, must emerge dynamically from microscopic local Beebles at all scales.
There isn't a magical boundary where quantum weirdness suddenly turns into a solid wooden table.
Exactly. There must be a mathematical state, which Bell denoted as fundamental variables psi and x, that applies to the whole world. And the classical observation emerges from that state.
Let's map this abstract physics directly to the CPCS MVC framework in Python, because this is the core architectural truth of our deep dive.
Okay, let's map it.
First, we have the model. In CMU CS Academy, this is the global app state.
This is Einstein's axioms A. It is John Bell's fundamental variables psi and x. The app object holds all the raw data: positions, velocities, masses, energy levels.
It is pure, raw math.
It has no color, it has no shape, it has no pixels. It is the hidden theoretical reality of the simulation.
Second, we have the controller. This is the on-step function.
This represents the rules of the universe.
Yeah.
This is where the physical laws are applied. The controller reads the Model A, applies the equations, and calculates the new state.
It is generating Einstein-specific statements S. It is the engine of time pushing the math forward.
Yes.
And finally, the view. This is the redraw app function.
This is Bohr's classical observation. This is Einstein's immediate experience as E. The view looks at the abstract mathematical model, reads the data, and collapses it into a macroscopic measurement on the screen.
It translates theoretical variables into colored pixels.
And this brings us to the golden rule of CPCS MVC mode. The expert source report emphasizes this, above all else, separation of concerns.
Calculating physical dynamics during the drawing phase is a strict MVC violation.
You cannot change the fundamental state of the universe merely by the act of drawing it.
If you put a line of code inside redraw that changes a particle's velocity, even accidentally, you are suggesting that the act of a human looking at the monitor physically changes the momentum of the object.
Which is a terrible way to run a physics engine. It causes massive instability. State calculations must run inside the controller loop on step, while rendering must be handled exclusively by the viewhook redraw.
It is a rigid, beautiful enforcement of the ASE paradigm.
It really is.
Okay, so we understand the philosophy. Let's actually build this universe in code. Every universe needs a Big Bang, right? It needs initial conditions.
Right. In the CMU CS Academy framework, those initial conditions, the global configuration parameters, are initialized inside the on-app start controller.
Let's guide the listener through setting up this initial state. The app object is literally the container for our reality. But before we even add our own custom physics variables like gravity or friction, the framework provides predefined properties for the sandbox.
And these aren't just cosmetic, they serve crucial computational and philosophical roles. Let's look at app.width and app.height. By default, they're both set to 400.
400 by 400 pixels.
Right. But computationally, these define the horizontal and vertical boundary limits for coordinate clipping. In physics terms, this is the spatial horizon of our isolated quasi-system.
Wait, remember Laplace's demon? Reason number 3 why the demon fails is horizons. The speed of light limits what we can know.
Exactly. We cannot simulate an infinite universe because we don't have infinite data.
Yeah.
We have to define a boundary.
Yes. By explicitly setting app.width and app.height, we are mathematically defining the limits of causal influence in our code.
This is absolutely essential. If you don't define the spatial horizon, the physics equations have no grounding. Where does a particle bounce? How does it know where the wall is? Where is the floor that the gravity vector is pulling toward?
The width and height define the boundaries of reality.
Next, predefined property, app.background. The default is none.
This establishes the vacuum of our simulated space. It is the void upon which our local beebles will eventually be drawn.
And the most important one for defeating Laplace's demon, app.steps per second. The default is 30.
This dictates how many times the on-step controller is called every single second. Philosophically, this is our time step, delta-ny.
Let's unpack why this defeats the demon. Laplace's demon requires continuous, perfectly smooth time to calculate infinite trajectories using calculus.
But human computers can't do continuous math.
They cannot. Compute limits. Reason number 2, why the demon fails. A CPU has to process discrete chunks of data. By discretizing time into 30 chunks per second, we avoid the impossible computational load of continuous infinity.
We accept a microscopic approximation, the universe freezing and jumping forward 30 times a second in exchange for macroscopic stability.
So on-app start is our Big Bang. We are setting the universal constants, the speed of time, the dimensions of the physical space, the nature of the vacuum before the first simulated atom even exists.
And once the universe is initialized, we have to set it in motion. Which brings us to the pulse of reality, the dynamics.
Let's dive into the on-step controller logic. This loop runs 30 times a second. It reads the current state, calculates the physics, and mutates the variables.
But how do we simulate real physics? We don't just want objects moving in straight, boring lines like an old DVD screensaver. We want complex, realistic motion. We want orbits. We want gravity.
For this, we turn to the source material on dissipative Riemannian mechanics.
Okay, pause. Dissipative Riemannian mechanics. If I'm a high schooler hearing that, my brain just shut off.
Fair enough.
We need to do an ELI 5 explain. I'm 5 on this math. What is a Riemannian manifold in plain English?
Okay, think of a Riemannian manifold simply as a warped 3D landscape. Imagine you are holding a large wok, or like a very curvy bowl.
Okay, a wok, I can picture that.
The surface of that bowl is the manifold. The path of a particle traveling on this surface, say, a marble rolling around the wok, is characterized by its energy.
2 types of energy, right? Kinetic and potential.
Exactly. The kinetic energy is related to the velocity of the marble, how fast it's rolling. The math uses a metric tensor to figure this out.
Metric tensor.
Which is just a fancy way of saying a ruler that curves perfectly along the surface of the wok, so you can measure distance accurately on a curved plane.
Okay, that makes sense. And the potential energy?
The potential energy corresponds to the lost surface, or in physical terms, gravity. It's the height of the marble on the side of the wok.
The text mentions the Euler-Lagrange equations. How do those fit into the woke analogy?
The Euler-Lagrange equations are the math that dictates the acceleration of our marble. They derive from the principle of least action, guiding the marble's motion toward the steepest descent.
So they pull it down.
Exactly. To calculate this, the equation looks at two things. First, the gradient, which is simply the direction straight down the slope. Second, the Hessian.
The Hessian, another scary word.
Don't let it scare you. The gradient tells you how steep the slope is right now. The Hessian tells you how fast the slope is changing.
Oh, I see.
Is the bowl getting steeper as you roll down or flattening out? The Hessian measures the curvature.
So the Euler-Lagrange equation takes the gradient and the Hessian, calculates the exact gravitational pull on the marble, and updates its velocity vector.
Spot on. But the sources highlight a massive problem with this pure system, the problem of the free particle.
Right. If our marble has no external forces acting on it besides gravity, and it's rolling around in a completely frictionless woke, the total energy of the system is perfectly conserved.
It just trades kinetic energy for potential energy.
It rolls down the side, gains massive speed, crosses the bottom, rolls up the exact same height on the opposite side, stops for a microsecond, and falls back down.
Forever. A particle with non-zero initial velocity governed purely by these equations will never, ever come to rest. It will oscillate indefinitely around the local minimum, the bottom of the bowl.
And in a physics simulation or a machine learning optimization, if things never settle, you've got a chaotic mess. The CPU is calculating maximum velocity vectors endlessly. It's visually jarring and computationally expensive.
So we have to introduce a secret ingredient. The text outlines it clearly. We must code a dissipation function. Friction.
We have to break the law of conservation of energy on purpose.
Yes. We introduce a dissipative force that continuously removes energy from the system, leaching it out of the math, so the marble eventually settles at the bottom of the woke.
But here is the genius part from the paper. It can't just be a flat, constant friction, right?
Correct. The source specifies that the friction must be speed-dependent.
Meaning, the faster the marble is moving, the harder the friction hits it. The text says the dissipation strength depends on the Euclidean norm of the intrinsic velocity.
Which is just a math way of saying how fast it's going.
Yeah. But there's a second part to this friction that is even more mind-blowing, mathematically speaking. The friction also depends on the angle between the velocity and the gradient.
How does that work?
This is the core of the DIMS dissipative Riemannian mechanics sampler mentioned in the text. The energy dissipation is maximized when the velocity is proportional to the gradient.
I'm trying to visualize this. The gradient is pointing straight down to the bottom of the woke.
Yes. If the marble is barreling straight down the steepest part of the slope, meaning its velocity vector aligns perfectly with the gradient vector, the math kicks the friction up to maximum to act as a brake.
Oh, to prevent the marble from vastly overshooting the bottom.
Exactly. But what if the marble isn't rolling straight down? What if it's traversing across the side of the woke, kind of circling the drain?
That means it's moving perpendicular to the gradient. It's moving along a level set. In that case, the gradient-aligned friction drops to zero, and the dissipation only depends on the speed, slowing it down much less.
That is incredibly elegant. It's an intelligent friction.
It really is. It breaks hard when plummeting down into a valley so it doesn't overshoot, but it allows the particle to explore the contours of the landscape smoothly.
And by writing the specific logic into our on-step controller, we guarantee our simulated objects will eventually converge to a state of rest in a finite amount of time.
Exactly. It saves the CPU from infinite chaotic oscillation.
Speaking of saving the CPU, I have to raise a massive red flag here.
Uh-oh.
I'm thinking about the real-world application of this. You just told me that 30 times a second, for every single object on the screen, our Python code has to calculate the Riemannian gradient, the Hessian curvature, the Euclidean velocity norm, and the gradient-aligned dissipation vector.
Yeah.
If a high schooler puts 100 bouncing balls on a complex curved terrain, that laptop is going to melt into a puddle of plastic. How on earth do we handle complex geometries without completely maxing out the compute limits we just talked about?
That is the perfect question, and it is the exact bridge to our fourth source material, gauge equivariant convolutional networks.
Okay, gauge equivariance. Let's break this down. Start with the problem. Why is calculating the whole landscape so expensive?
In differential geometry, when you have a complex manifold, say a massively undulating 3D terrain, or a Mobius strip, it is mathematically impossible to define a single global coordinate system that works perfectly everywhere without distorting the math.
Think of trying to peel an orange in one piece and lay the skin perfectly flat on a table. It tears.
Or think of a world map. You can't make a flat 2D map of the 3D Earth without massively stretching Greenland and the poles.
Exactly. If you try to force a global 3D coordinate system onto complex curvature, the math becomes bloated and computationally devastating.
So instead of a global coordinate system, mathematicians use local charts.
Local charts.
Imagine taking tiny, overlapping rectangular patches of that orange peel. Individually, each tiny patch is small enough that you can treat it as basically flat. The choice of local coordinates inside one of these tiny patches is called a gauge.
So it's a local reference frame.
Right. But if the physics are real, they shouldn't depend on an arbitrary choice of local coordinates. The outcome must be the same, regardless of the local reference frame. That principle is called being gauge equivariant.
Okay, so how does this save my laptop's CPU?
Because by utilizing gauge equivariance, we don't need to calculate the massive Euler-Lagrange equations using a global, highly complex metric tensor for the entire universe. We can process the physics locally, inside a small neighborhood, a local gauge.
So we just do the math for the immediate surrounding area of the particle.
Yes, the network restricts the math to a neighborhood small enough that every point is connected by a unique, simple path called a geodesic. And then we use an incredible mathematical tool called parallel transport.
I need an analogy for parallel transport.
Okay, imagine you are standing in a massive winding hedge maze on a hill, trying to calculate your exact GPS coordinates relative to the center of the Earth. Factoring in the curvature of the hill just to figure out how to take 5 steps forward would require massive brain power.
That's the global coordinate system.
Right. But instead, you use a local gauge. You just say, from my current perspective, the path is 5 steps forward and 2 steps right. That math is incredibly simple. Flat space integration.
But what happens when the path curves? My perspective changes. Forward is now pointing in a different global direction.
Yes. But as long as you know how your perspective shifts when you turn the corner, that specific translation of your internal compass, you don't need the global GPS.
Okay.
That shift is parallel transport. It's a way of sliding your local coordinate vector along a curved surface while keeping it locally oriented.
So in the code, instead of computing the Hessian for the entire 3D mesh, we just compute simple flat space 2D math in the local tangent space right next to the particle and use parallel transport to stitch those local answers together as the particle moves.
Precisely. The physics remain coordinate, independent, and accurate, but the computational load drops exponentially. You are solving simple local equations instead of massive global ones.
Unbelievable. Okay, so look at where we are. We've got our hidden universe initialized in on-app start. We've got our physics calculating efficiently 30 times a second in OnStep using dissipative friction and local gauge parallel transport.
A hidden backend is humming. The math is flawless.
But the screen is still pitch black.
Which brings us to the culmination of Einstein's philosophy, the act of observation.
This is the most visually dramatic part of the CPCS MVC framework, redrawal app.
This function is triggered by the framework every single refresh cycle, immediately after OnStep finishes calculating the new state. And the very first thing it does, it completely clears the canvas.
The universe is wiped blank. Every 33 milliseconds, absolute void.
It is an ephemeral canvas. Because we are not in CS1 persistent mode, absolutely nothing survives the cycle. The view must reconstruct the visual scene from scratch using transient functional drawing primitives.
The tools we have at our disposal are purely functional verbs. Draw rect, draw circle, draw line, draw label, draw polygon. You call them, they flash onto the screen, and then they are immediately forgotten by the computer's memory. They do not persist.
Now, let's tie this back to John Bell and Niels Bohr. Bohr said the account of all evidence must be expressed in classical terms. Bell said we need macroscopic local beebles, pointers on a dial that are intersubjectively testable.
These drawing functions are exactly that. They are our macroscopic local beebles in Python code.
They are. In redrawal, we are taking the abstract, coordinate-free, continuous mathematical data residing in the global app object Einstein's axioms, and we're forcing it to collapse into a specific, observable, macroscopic coordinate representation on the 400 by 400 grid.
We are collapsing the wave function.
Essentially, yes. The mathematical model in the app object could represent a particle's position with infinite decimal precision. X equals 150.394857, but draw circle forces you to choose a specific integer pixel coordinate to physically light up on the monitor. It is the physical measurement.
I want to use an analogy here because this is my favorite way to visualize MVC. It's like a strobe light in a dark room. Think about it. The physics All those Euler-Lagrange equations, the friction, the parallel transport and on-step, they are happening in the pitch black. The math does not emit light.
The back end is entirely invisible.
Redraw is the flash of the strobe light. It doesn't create the motion, it doesn't calculate anything, it just brightly flashes for 1 millisecond, revealing exactly where the mathematical objects are at that exact moment, and then it goes dark again.
And this brings us back to the fatal MVC violation. What happens if you try to put a line of code that moves the ball inside the redraw function?
Damn, fatal error. Because you were trying to change the physics with the strobe light.
Right.
The strobe light is just a passive measurement. You cannot reach out and move a moving object while the flash is going off. The measurement is a passive observation of the hidden state.
The separation of S, the specific statements of theory in the controller, and E, the immediate experiences of observation in the view, is literally mathematically enforced by the Python compiler. It's a beautiful thing.
It really is. Now, for our Sigma scholars out there who are building their final projects, they're going to want to build something bigger than just a single 400 by 400 physics sandbox.
They want polished applications.
Right. They want a configuration menu where a user can type in the gravity coefficient, click a start button, and then enter the physics sandbox.
Which requires an understanding of multi-screen architecture.
How do we build that? How do we route between different worlds?
The CMU CS Academy framework provides specialized routing controls for this. Instead of initializing the app with the standard run app constructor, we initialize a multi-screen application using run app with screens, initial screen name, passing the name of the starting menu screen as a string.
But here is the critical part, and the source material issues a massive warning about this. The global app state is shared across all screens.
This is vital. Remember, there is only one true underlying reality. If the user on the setup menu sets a variable, say app.friction, equals 0.5, that is stored in the foundational axioms.
When the user transitions to the active sandbox screen, the on-step physics solver reads that exact same app.friction variable. It is a single unified backend.
And the warning in the text.
Only use a single on-app start initialization pass. Do not try to write a separate setup function for the menu and a separate setup function for the sandbox.
Defining multiple setups causes alphabetical execution order conflicts across the screen scopes. You'll end up overwriting your universe's physical constants unpredictably.
One big bang per universe.
Got it. So how do we actually handle the code on different screens? If OnStep runs the physics, but I'm on a menu screen, I don't want the physics running yet.
Event routing. Each screen gets its own handlers, strictly named with a prefix, screen name event handler.
For example, menu on mouse press or sandbox and step.
Right. The framework automatically routes the input exclusively to the active screen's handlers.
And to move between them, you call cActive screen name. This instantly switches the active screen, reroutes all incoming events, and triggers a very special lifecycle hook, screen name on screen activate app.
Okay, I have to stop you because my brain is connecting two completely different sources right now.
What's that?
This multi-screen routing, switching from a menu to a sandbox, it sounds exactly like changing our reference frame in physics. Is switching screens mathematically equivalent to a gauge transformation?
If we synthesize the sources, yes. That is a brilliant connection. Think back to the gauge equivariant networks and the Mobius strip.
Okay.
The Mobius strip has a twist in it. You can't cover it with one flat local chart. You need at least two overlapping charts.
Right, to handle the twist.
When a feature field like our simulation data moves from the first chart to the second chart, it crosses the overlap boundary. The neural network has to perform a gauge transformation to translate the data from the first reference frame into the second. On Mobius strip, because of the twist, this requires a specific math operation the paper calls transport padding, where the data is actually reflected or scaled as it transitions to the new local gauge so it doesn't break.
Whoa. So when I write cActive screen sandbox in Python, I am crossing the overlap between charts.
Precisely. Switching screens changes how the observer interacts with and views the underlying global app state. The mathematical reality in the app object remains exactly the same, but the UI layer, the observation layer, the local gauge, transforms perfectly to the new reference frame.
And how do I code that transport padding in Python? What does that actually look like for a high schooler?
It happens inside that lifecycle hook we mentioned. Screen name on screen activate. Let's say your menu screen allowed the user to input a gravity value between 1 and 100 on a slider.
Okay.
But your physics engine needs a gravity vector between 0.1 and 1.0 to remain stable. Inside Sandbox on Screen Activate app, you would write the transport padding math.
Yeah.
You take the user's app.manyGravity slider variable, divide it by 100, and assign it to app.activeGravity.
You translate the data into the specific local requirements of that new screen before the strobe light flashes again.
You prepare the UI for the new perspective without corrupting the raw data. The observer changes, but the hidden universe remains constant. It is the ultimate implementation of coordinate-independent physics.
It is the architectural realization of everything Einstein and Bell argued for, executing seamlessly in Python.
Unbelievable. What an absolute journey. Let's synthesize the epic path we just took, scholars.
We started with the foundational philosophical debates of the 1920s. Einstein correcting Heisenberg's flawed verificationism, proving that you cannot base reality solely on what you print to a screen. The theory must dictate the hidden backend.
We saw how standard CS1 persistent graphics completely fall into Heisenberg's trap, conflating the drawn pixels with the mathematical state, leading to accumulation errors and physical impossibilities.
We escaped that trap by embracing the rigid, mathematically pure CMU, CPCS, MVC architecture. We mapped it directly to John Bell's local Beebles and Bohr's classical observations. We permanently separated the hidden mathematical universe, the app object, and the on-step controller from the macroscopic measurement, the redraw view.
We brought in dissipative Riemannian friction to ensure our simulated particles converge elegantly into valleys instead of oscillating forever, maximizing energy loss along the steepest gradients. And we defeated Laplace's demon and CPU limits by using local gauges and parallel transport instead of global coordinates.
And finally, we utilized gauge transformations via multi-screen routing and on-screen activate transport padding, allowing the observer to smoothly transition between different interactive reference frames without ever corrupting the underlying global state.
We built a flawless physical simulation by coding the literal philosophy of quantum mechanics. Scholars, Boost and Sigma scholars of Edward Little High, we want to thank you for embarking on this insane journey of computer science and quantum philosophy with us.
You guys have the intellect to not just write code, but to understand what that code actually means for the architecture of reality.
It's an incredibly empowering way to view programming. You aren't just typing syntax to make a ball move. You are defining axioms. You are calculating statements. You are architecting universes.
But before we let you go, we want to leave you with one final provocative thought. Something to mull over as you stare at your screen, writing your next physics engine.
We've established the rhythm of this universe. The physics update 30 times a second in the hidden controller loop, on step. And the screen is wiped and redrawn 30 times a second in the view, redraw.
The physics happen in the dark, and redraw is the strobe light that flashes to reveal them.
But consider this. Because of the processing time of the CPU itself, there is a literal microsecond gap between the end of the on-step execution and the beginning of the redraw execution.
A microscopic fraction of a second where the code has finished calculating the math and is just about to trigger the drawing function.
In that exact microsecond, the app state has mutated. The hidden mathematical universe has moved forward in time. But the screen has not yet been drawn. The photons haven't been emitted. For that infinitesimal fraction of a second, the universe has moved, but no observation exists.
If your code generates a fatal error in that exact gap, say a memory leak triggers right before redraw is ever called, the program terminates instantly, the strobe light never flashes.
Did the simulation in that final unobserved frame truly happen?
Ponder that as you code your next universe.